Today, we are going to talk about Apache Spark. Let's start with a problem. Imagine you have an SQL script to run, but it takes ages for it to execute. Maybe you have some training data that you want to fit into a machine learning model, but the dataset is too large for your computer to handle.
Computer says no.
So what's the solution for this? One obvious thing we can try out is buying a better computer. But as data grows by time, it can get really costly to upgrade. In the early days, a framework called Hadoop MapReduce was used to handle big data problems. One major issue was it created bottlenecks due to the data being read from the disk. To overcome this, Apache Spark was developed. Apache Spark is an open source data analytics engine that can process massive amounts of data from multiple different sources. It was developed by Matei Zaharia in 2009 at the University of Berkeley. In 2010, the project was made open source, and in 2013, it was donated to the Apache Foundation. The base of Spark is an RDD, or a resilient distributed dataset. This is a collection of immutable or read-only objects. This is essentially what Spark uses to break huge datasets down into more manageable pieces. When RDDs are copied and chunks are broken down into partitions, one benefit of this is if one partition crashes, without going back to the original source of the data, we can recover the RDD quickly. These partitions are sent to a cluster of computers and are processed parallelly. You might think this is a waste of space, but Spark manages this with a clever technique. It doesn't actually make copies of the transforming data, but it only keeps a track of what to do with the data. So when an output is requested, it can follow the tracked changes. Let's see what happens under the hood. There are two main parts, drivers and executors. When Spark program runs, a Spark context is created. This decides what needs to be done, where it needs to be done, and how. At the end, it comes up with a set of instructions and transactions. These instructions are in the form of a DAG, a set of logical instructions. The directed acyclic graph, or DAG, translates these instructions into an execution plan, which is basically a smaller set of tasks. The Spark context requests resources from the cluster manager. The cluster manager then allocates the resource, and each executor executes the task. The results are then sent back to the driver. For a better understanding of this, let's take an airport. The air traffic control tower navigates multiple different flights similar to a cluster manager. The operational staff of one single airplane is responsible for what goes only within their plane, similar to the Spark context. One individual flight is a Spark job. While the plane has taken off, all the internal tasks within the job is managed by the Spark context. How that flight and many other flights navigate in the same airspace without collision is managed by the cluster manager. All of this together is what is called the Spark core. On top of this, there is a layer of libraries. Spark SQL for structured and semi-structured data processing, streaming enables real-time data processing, MLlib provides tools for scalable ML workloads, and GraphX supports graph computations. All of this supports multiple different languages such as Python, Java, or Scala. Below the core is what does the actual heavy lifting. Hadoop Yarn is a resource negotiator. Amazon EC2 is cloud infrastructure providing virtual servers to run Spark. Apache Mesos is a distributed resource manager, and Kubernetes is a container orchestration platform. What are the advantages of Spark over other big data solutions? One main thing is speed. Since the data is processed in memory, it's way more efficient. Flexibility. Programmers can code in multiple different languages. Streaming allows near real-time data processing. And finally, the ability to support machine learning workloads. That's all for the video, and thank you for watching.